Let's do it. Good afternoon, everybody. Well, it's afternoon here in Alabama. I guess technically if you're west of me, it might not be afternoon yet, but just hit noon, so technically it's afternoon here. Gorgeous weather in Alabama. I hope that everybody else has nice weather this afternoon. I appreciate you joining us on our AP Stats CRAM. Today we are going to continue looking at inference, and we are going to take the turn going from proportions and categorical data to quantitative data with means. And there's a lot of similarities between these two, so I don't want to bog things down and continue looking over those same things that we've already covered in previous streams. So we are going to do some activities today. I'm looking forward to that. Make sure you use the chat. Let me enable that real quick. So yeah, make sure you use the chat. Also the Q&A option from Vimeo. Make sure you use those things if you have questions. Either me or my awesome TA Sander is kind of moderating those things and making sure that we are, on the same page. So again, it's being recorded every time, just kind of a disclaimer there. So know that if you want to change your name to something generic, then that's fine. Social media, I've seen a lot of great tips for AP Stats being posted on the Fiveable Twitter feed, okay? I am not on Instagram or YouTube. I think I do have a YouTube channel, but I don't ever do anything with it. So, but I am on Twitter, and I keep up with Fiveable there, and there are all sorts of great resources that you can just quickly read and kind of get an idea for AP Stats and, of course, other subject areas as well. So Twitter is awesome. The Fiveable team puts great test-taking tips out there and things like that. So coming soon, so the second half of this stream where we talk about hypothesis tests is going to be next Saturday at 2 p.m. Eastern Time. The Unit 7 trivia is the next day, so that's Sunday, April 25th at 6 p.m. Eastern Time. Those trivia questions are designed to give you some basic multiple choice practice and make sure that you have the big picture from the units, so definitely take advantage of those as well. And then, of course, our 5-hour CRAM finale on Sunday, May 16th at 1 p.m. Eastern Time. I'm super excited about that. I think that a lot of you are going to go from a 3 to a 4 or a 4 to a 5 or maybe even a 2 to a 3 just from the experience you're going to have during that CRAM finale. Not that it's anything that I'm doing, but you putting forth the effort to show up the day before the exam and really hone in on some skills and just tweak a few things right before the exam is going to be the difference in scores for several of you. So I'm super excited about that. Already kind of thinking about how that's going to go, and yeah, it's going to be awesome. Super excited. I know I'm stressed with AP CRAM season. I know you are all too, but we're going to get through it together. And that 5-hour CRAM finale, we're going to come together one last time and make things happen. Okay, the magic is going to happen on that day. I'm confident. All right, so in this stream, we're going to quickly review confidence intervals. We're going to look at that process of confidence intervals again, the conditions, a little bit different with means, the type of interval also a little bit different, and kind of how we're going to work through that. And then we're going to look at an example, okay? We're going to look at just some, go a little bit deeper into what a confidence interval is and what it's going to do for you, where to use it, what it means, what the different terms represent, and how we can interpret those. Interpretation is huge, so we're going to look at that. So I see in the chat, if I can get from a 2 to a 4, I would be blessed. Man, that would be awesome. Same here, any improvement is good. One thing to remember about AP Stats, which is really awesome, I like the fact that most colleges do it this way, is that I think every college I've looked at, and I haven't had any students going to, Ivy League colleges and things like that, the really upper echelon, but most colleges that my students go to, they're like, what do I need to get credit? So I'll go to the college website and look it up. A 3 is the same as a 4 is the same as a 5. I've had students make 5s that I felt like probably were pretty close to perfect. Last year, I had 2 students make a 5. Both of them attended the 5-hour CRAM finale. I was not leading it last year. It was on my birthday, so I took the day off. Another AP Stats teacher led that, and both of them made 5s on the AP exam. In stats, of course, last year was weird, but the students that I had that made a 3 are going to get the same college credit, more than likely, than making a 5. So just keep that in mind. There's not, I know with AP Cal, you can get Cal 1 and 2 credit, or maybe some colleges just give pre-Cal credit for a 3 and AP Calculus AB. So in stats, 3s get degrees, all right? So it does take a little bit of the stress off, for probably most of you, knowing that your college is going to accept a 3 just like they would someone who makes a 5. Now, if you make a 5, and I think that's a great goal to set, then, virtual high five, go for it. But a 3, 4, 5 most of the time means the same thing. So a little bit of pressure off there. And I'm confident in everyone here that we can achieve that goal. So confidence intervals, what is the big thing? So we have 2 options with inference. We can either predict a population parameter or we can test a claim, okay? And the confidence interval is the prediction part, or the estimation part. So we're going to take a sample, okay? And that is our middle of our confidence interval. And then we say, well, what if our sample was a little bit wrong? So we're going to say, well, let's give it some buffer zone, okay? We want to predict that true value. So what we're going to do is we're going to add a little bit. I think I did that backwards because I'm mirrored here, okay? And then we're going to subtract a little bit and say, yeah, we'll give ourselves a little bit of buffer there, adding and subtracting. And then somewhere in that interval, that is going to be our confidence interval. And we are pretty confident that that confidence interval is going to contain that population parameter that we're looking for, whether that's a mean or whether that's a proportion. Okay, so that's kind of I want you to picture with a confidence interval, is that you have your sample statistic from the data you gathered, and then you're adding and subtracting. I did it backwards again. You're adding and subtracting something to that interval to give you some buffer zone about where that population parameter is going to be. Okay, it is used to estimate things. The buzzword on FRQ questions is usually create and interpret a 95% confidence interval. It's very clear that that is the process you're going to go through. And of course, just like with anything in statistics, the larger our sample size, the better our estimate is going to be. Okay, so if I take a sample of 30, you can make a confidence interval with that, but our confidence interval of 10,000 is going to be a lot better. And it just popped into my mind, one of the things about like the COVID vaccine trials that makes the data very good as opposed to other clinical trials is that there was like 30,000 people who signed up. So that makes our data way better. That's why they're so confident that they are safe. And I know there's been some issues with the Johnson & Johnson vaccine, but the sample size was so large that they were able to take care of safety efficacy within maybe a shorter time period because so many people signed up for the clinical trials. I've heard from doctors that I had to speak to my class about that sort of idea, that normally you really need 300 or 400 in your sample size to get a good margin of error. He's like, you can get a pretty good safety estimate and a good margin of error with 300 or 400 participants in a clinical trial, which is generally pretty easy to get. And he said with the COVID vaccine trials, they were getting 25 and 30,000. So way larger. That brings that margin of error down, okay, which means that confidence interval, where the margin of error is that buffer zone. So it minimizes that, and it hones in on that true efficacy rate of the vaccine a lot better than if they were only able to get 200 or 300. And this was our formula that we used for proportions, okay? So we took our sample proportion. What was the proportion from our sample of 100? we added or subtracted a z-score, and then we multiplied it times our standard error, and that together made the margin of error. Okay, so this was what we did 2 weeks ago, or a week and a half ago, whenever our last stream was, on confidence intervals for proportions. So what we're going to do today is we're going to take a turn on and look at it in terms of means. Okay, I see in the chat, Ryan, can you repeat on the buffer zone margin of error? I'm a bit lost. Okay, so the buffer zone, or the margin of error is the more statistical word. That is the stuff that we add or subtract to our sample proportion. So let's say we took our sample, we'll go back to the COVID vaccine. Let's say that the group that got the vaccine versus the placebo was 90% less likely to get sick. Okay, so from our sample data we have 0.9, 90%. Okay, now we know that that's not really going to represent everybody in the world. Okay, so we want to give some sort of a buffer to that. And I've seen some articles that say, you know, the Moderna vaccine is 90 to 95% effective. Okay, so you know there's an interval there. So we have our sample proportion. All right, and then we take all this stuff after the equal sign. We calculate a z-score based off of whatever confidence level we want, and then we calculate our standard error. These are both on your formula sheet. Okay, and we'll look at the formula sheet in a few weeks as well. And you multiply your z-score times your standard error, and that gives you a buffer zone. So that gives you an amount you can add to that 90% efficiency and subtract to that 90% efficiency. You know, and let's say that margin of error comes out to be 2.5%. Okay, so we could say a vaccine is 87.5% efficient to somewhere between 87.5 to 92.5% efficient, which we know that's really good. So the margin of error is that stuff that we add and subtract to our sample proportion. Or today we're going to look at sample mean. That's just kind of a quick review from a few weeks ago. So if it asks you to calculate the margin of error, you're taking that confidence interval formula and calculating the two things, your test statistic, either your Z or your T-score, times your standard error, which those are on your formula sheet. That breakdown of a confidence interval is on there. I hope that answers your question on the margin of error. That is the bit you're adding and subtracting to your sample estimate. Okay, so we have a process to follow. The first thing we need to do is we need to state what we are estimating. In this case, we're going to be estimating a sample mean. We need to plan. We have conditions for inference. There are certain things that in order to use that formula that we just looked at, and you might remember this from a few weeks ago, there are certain things we have to do in order to make sure that that formula is accurate. Okay, then we do the calculations, which is typically in our calculator. And then we conclude, okay? That is, in AP Stats, that's one of the biggest things we have to do. Interpretations are always necessary. A number with no work and with no interpretation doesn't really do a whole lot for someone reading your your paper. So if you get a confidence interval, well, what the heck do those two numbers mean? And they generally, on the AP exam, on a free response question, they cue you for that. It doesn't just say create a confidence interval, it says create and interpret. So what do those two numbers mean? What does that lower and upper bound mean? Okay, so for means, we talked about all four of those steps a few weeks ago, but for means or quantitative data, there are some slightly different aspects, and we're really just going to focus on those and then go through some problems. Okay, so when you are stating, you need to start by letting the reader know exactly. I see in the chat, we are blank % confident that the true mean or proportion is between blank and blank. Okay, just context, all those things, we'll get there in a minute. But that is the interpretation. That is your can statement, is what I like to call it. So just as we did with proportions, You need to start by letting the reader know what it is you're estimating. So with looking at means, we are estimating the true mean test scores for all AP Statistics students. We need to let them know, let the reader know what exactly it is that you are estimating with your confidence interval. Okay, so when we are planning, in the chat, what are the 3 conditions for inference that we have discussed so far? I'll let you all answer. We are on it today on a Sunday afternoon. Random, independent, normal. Ryan, what you said, large count, 10% condition, and random, that is good also for proportions. The large count condition only works with proportions, and we'll talk about that, but you are completely correct in that as well. So our formula always hinges on these 3 conditions. Everybody said random. That's fantastic. There's no way to fix not having a random sample. If you take a biased sample, your result is going to be biased. And that is a huge, huge problem. Okay, so we have to make sure that our samples were selected randomly. Okay, and we have to make note of that. The best way to do that when working out a problem is to quote the problem, and we will practice that in just a little while. The next thing is independent, which is the 10% condition. Then we have to make sure that our population, actually that should be sampling distribution is approximately normal. Sometimes we don't know that the population itself is normal, but our sampling distribution would be. So with means, I see what I was going for here now. So if our population is normal and that's given in the problem, that means that our sampling distribution is normal. So you can use that as your normal check for means. You can quote the problem again and say the distribution of yada, yada, yada is approximately normal. If your problem says that, you can just quote the problem just like you do random. And that means your sampling distribution is normal. Okay? Or we can use the central limit theorem. A lot of people say that's the fundamental theorem for statistics. What does our sample size have to be in order to satisfy the central limit theorem? I'll let you guys answer in the chat. Sample size more than 30 or equal to 30. Some textbooks even use 25. And I think we did an applet a few weeks ago that used 25. But 30 is what AP Stats generally uses. Greater than or equal to 30, your sampling distribution is normal. So one of those 2 conditions, or sort of your last ditch effort, which we're actually going to need today, and I believe next week too, is there is no skewness or outliers in the sample data. Okay, so if you happen to, let's say you have a sample size less than 30, your population, it doesn't say anything about your population being normal, then you can sketch a box plot and make note that there are no heavy skewness or outliers. And you might have a little bit of skewness, but you don't want something that's like super lopsided. You know, one tail is 4 times as big as the other. A somewhat symmetric distribution is what we're really looking for. Okay, and I really hope that the example we're using today doesn't have outliers. I'm a little bit nervous about that, but we'll see what happens. If not, we'll continue the problem and just make note of it. So yeah, so the easiest way to sort of break that down is central limit theorem is the easiest because you can literally just say 65 is greater than 30, parentheses, central limit theorem. Okay, that's the easiest. It's also the most likely option that you're going to use for that normal check. However, if your sample size is too small, look in the problem to make sure it doesn't note that the population is normal. And then if it doesn't make note of a normal population, then you need to enter your sample data or pull your sample, pull it from your problem and make a box plot and show that it's somewhat symmetric. Okay, that's kind of your last ditch effort, but it does show up. It's been on the AP exam a handful of times, so it is important to know. Central limit theorem is the easiest and most likely. Normal population occasionally shows up. It's also easy. You just have to quote the problem and then the skewness and the outliers. So if we're thinking back to proportions and thinking back to those conditions, random is the same for proportions or for means. Okay, independence is the same for proportions and means. The normal condition is different. So if we're going through that state plan do conclude, the conditions, if you're looking at a mean versus a proportion, is slightly different. All right, you're not going to use large counts for means. I'll repeat that. You're not going to use the large counts condition for means. You are going to use central limit theorem or something else from the problem as noted over on the slides. Okay. If it is proportions, you cannot use central limit theorem. You have to do the NP greater than or equal to 10 in 1 minus P greater than or equal to 10. And there are some differences in the way you handle that based off of if it's a hypothesis test versus a confidence interval when there are two proportions. And we talked about that last week. So, if large counts condition is something that you're still confused on, go back and look at that. There's also great study guide resources you can go and look at. So that's our first difference in that state plan do conclude for means versus proportions, is that the normal condition is different. Okay? So we already actually mentioned that. So it states that as long as our sample size is at least 30, our sampling distribution will be approximately normal. We looked at that in the Unit 5 CRAM for sampling distributions. We did that cool applet where we drew out weird distributions for the population. We pulled out the sampling distribution of a sample size of 5, 10, and I think 25. And as we increased our sample size, our sampling distribution became more and more normal. Yes, the normality test is swapped for proportions to means. We are not doing large counts if we are looking at quantitative data or we're trying to estimate a mean instead of a proportion. We are going to use central limit theorem instead of large counts condition. Okay, so here you have a population that is skewed to the right. If we take a sample of 30, if we take every possible sample of 30, we would get a normal distribution as our sampling distribution. Okay, every possible sample of size 30 from this distribution would give us this. If we have a uniform distribution, our sampling distribution would be normal. If we have a bimodal distribution, all right, it is going to also be approximately normal. If we have a skewed left, it would be approximately normal. Of course, the one that's not on here is a normal population. If we take a sampling distribution out of a normal distribution, of course it's going to be normal. It's going to be a lot more honed in on that middle even because it is symmetric. Okay, all of those, as long as the sample size is large enough, okay, will result in a normal distribution because sample size greater than 30 yields a normal distribution regardless of what shape the data looks like. Okay, so here's the next change. When we are doing our data, so we did state and plan, the one difference was the normal check, and then whenever we get to the do part of our confidence interval, we are going to use a t distribution rather than the z distribution. Okay, so we use a z-score for our formula, a z-star for our critical value. With quantitative data, we are not going to use the z distribution. So we're not using the normal CDF, okay? We're using sort of a modified version of that based on our sample size, and the term they use is degrees of freedom. Okay, and here you have a graph of what the T curve looks like. Okay, so I'm actually going to swap. I'm going to get you a little bit bigger here so you can see it some more. So with 1 degree of freedom, that's the pink curve. And you can see it's a little bit more spread out. Okay, it goes all the way to a standard deviation of 4. All right, which we know a normal curve doesn't do that. It only goes to 3 or it only goes to 3 or 1. And the blue curve, you can see it starts to get a little bit more towards that standard normal curve, which is the black one. All right, it starts to shrink in a little bit more. Yellow, 8 degrees of freedom, a little bit more normal, and then 20 degrees of freedom. It is very, very close to that being exactly perfect. Okay, and then so basically the standard normal curve, the Z curve, is when you have an infinite degrees of freedom, which we will look at that in a few weeks. We're going to do one stream that it says it's only free response, but we are going to look at the reference page as well, and I'm going to show you some tricks on the reference page, the reference packet you get. Okay, that is a great question, Jay, in the chat. We only use T-star when we have a sample standard deviation instead of the population standard deviation. That is true. When you have a population standard deviation, you technically can use a Z-score for quantitative data. However, 99% of the time on the AP Stats exam, you're not going to be given a population standard deviation. You're going to be given a sample standard deviation, and therefore you would use the T-score. So in trying to get the most bang for your buck on the AP exam, means T-distribution, you're going to be right 99.9% of the time, and that's just easier to study for. Also, my thought is that if I know the population standard deviation for some strange reason, I probably know the population mean. And there's no point in doing a confidence interval to estimate the population mean if in fact I already know it. Maybe that makes sense. So I just think it's very rare that you would know the population standard deviation and still need to estimate the population mean. But that is a good little caveat there, a little small difference. I think it's best, if you're looking at a problem and you say, hey, this is quantitative data, I'm estimating a mean by doing a confidence interval, just use the t-distribution, okay? Use a t-test in your calculator. So yeah, as you get more and more, a sample size larger and larger, you get closer and closer to the standard normal curve, which is that Z curve. So to find your degrees of freedom, you take your sample size and subtract 1. And that is something you will enter in the calculator when you are doing your t-test in just a minute. Let's see. The reason why the degrees of freedom is n-1, because I know a lot of people have that question all the time. I still am trying to wrap my brain around that, but the best explanation I can come up with for why that is if I have a sample and I want my sample to have a mean of 30 or 28 or whatever, okay? If I want my sample to have a mean of 28, so I take everybody out of my, my sample of size 100, and I want it to their scores to average to be a 30. Okay, well, the first 99 people that I draw out for my sample, they can have whatever score they want. Okay, but that last person, it has to be a fixed score for that last person in order to get to my mean of 30 that I was trying to get to. Okay, so the first 99 people for my sample can be whatever they want. They are free to be whatever they want. But that last person is a fixed number that makes it come out to that mean that we want. That's really the best explanation I can think of on why we use n-1 for our degrees of freedom. Really best to just know it's n-1 for a t distribution. It's a little bit different for chi-squared that we'll get to in a few weeks, but for a t distribution, it is n-1. Okay. All right, so that is our do. Here's our formula. Okay, and again, there is that little caveat where you could use a z-score. However, we most of the time don't have that. So it's best, I think, in just the interest of more bang for your buck on the AP exam, to just use a t-score anytime there's a mean. So you take your sample mean, and then you add and subtract your margin of error, which your margin of error is your t-star, your t-score, based on that degrees of freedom, times your standard deviation divided by the square root of n. So that's your standard error or your standard deviation. And together, all of that plus minus makes out our margin of error. Okay, so again, those conditions come into play. It is important to have a random sample so that this is a good estimate for our population. All right, that scope of inference comes into play. If I take a random sample, it is reflective of that population. Therefore, I can use it to estimate so I can use it to estimate my population, which is the whole goal of a confidence interval. Our normal condition, that is so that we can use a t-star. So that we can use a t-distribution, I have to know that my sample is large enough. So that we talked about that condition. Central limit theorem, that's your first option. If that's not true because our sample's not big enough, then we want to go to our normal, see if there's something in the problem that tells us it's normal. And then if that's not true, then draw out a box plot to show there's no skew or outliers. That's usually when you're given a very small data set, which does happen. And then the independence condition is necessary so that we can check our standard deviation, the standard error formula. That is on your formula sheet, by the way. This formula is on your formula sheet. It's just written in a way that you have to understand it to put it together. And that's why we're going to go over that formula sheet, so that you don't have to remember this formula. Okay? Now, before I continue on the conclude, what tool are we given in AP Stats for the whole exam, not just part of the exam, that will do this formula for us? And I will let you all answer it in the chat. What tool are we given that keeps us from having to know this formula? It's definitely useful because multiple choice questions come into play, but on free responses. We have tools that make our lives easier. What is the one that makes this part a little bit easier? All right, think about if you're taking an AP Stats test, what are the things that you want on your desk to make sure you have everything you need? You have your test, you have something to write with. What else do you have? A calculator. A reference sheet is good, so the reference sheet does point you back to that formula. But a calculator is really what I was looking for, and we will go over how to do these in a calculator today. Okay, in just a second, we're going to look at some examples, and I'll show you how to do it in the calculator. I'll also show you the best way to set up your paper. I can mirror my iPad and actually write out the answer as opposed to just typing it up. So I can give you a good option of what your paper should look like on the AP exam. All right, yes, calculator, guys. Make sure you have your graphing calculator. Make sure it's fully charged. Make sure everything is good to go on that front because it saves your life. All right, so then our conclusion, we already discussed that earlier in the stream. This exact interpretation came up. We are blank % confident that the true mean of aluminum cans recycled is between 80 and 120 cans per day or whatever. Okay, whatever. I just saw my picture of me in a can stuck up there at the top. So that's the first thing that popped into my mind. So yeah, make sure you include context. Make sure you reference the confidence interval. Make sure you include context, which includes the units at the end. We didn't really need units for proportions because our answer was 2 proportions, and that was pretty clear. Also, make sure you make reference to the true mean or the population mean. Remember, we are trying to estimate what the population is. That's the big picture. We know what our small picture is, okay? It wouldn't make sense to say we are 95% confident that the sample mean of aluminum cans recycled is between blank and blank. Well, we have a sample that tells us exactly what that sample mean is. We are estimating the population mean, the true mean, based on our sample, okay? So make sure you make reference in some way in your conclusion to that big picture population mean. Usually saying the true mean is good enough for the readers there. And also context. Okay? I feel like the Fiveable Twitter team should make a tweet that's like, for AP Stats students. And then, like, you open up a thread, and the first thing on the thread is just context in big words. Maybe a GIF that says context. Just be reminded of that over and over and over again. Every answer has to have context in your interpretations there. Okay, and sometimes that's as simple as saying square feet. I was grading a test the other day. That was an old AP question, and literally if you just said, it was one where you cuss the data, and you could say the center is around 200 square feet, and you automatically get partial credit on that problem. One sentence, you said square feet, and you estimated the center of the distribution, and you would get half credit. You could have someone write out a whole paragraph that might actually tell you more about the distribution, and get less credit. So that was kind of mind-blowing to me, and that's what most teachers say, is state the center first and go ahead and include context, because then you have one sentence and you already have partial credit. And all partial credit on free responses gets you a 3, so as long as your multiple choice is kind of in that same range. So yeah, make sure you do that. So we're going to look at a little simulation here real quick. So this is the website. I will put it in the chat if you wanted to go there and play around with it. You don't have to. I'm going to share my screen in just a second. All right. So here is what we have. So, and a really awesome website. Just fantastic. So what we are going to do is we are going to estimate a confidence interval. Okay? We'll start with 1. So we are doing means. We are basing it off of a normal curve. Of course, this has things way beyond the scope of AP statistics here, and we are going to be just looking at the things that we're typically doing. And then we're basing it off of a t-distribution because we don't know the population standard deviation. Okay. So what we have here, all right, our sample mean is 18, or well, our population mean is 18. Okay, we'll say that. So that's our population mean. Our standard deviation is 5, and our sample size is 100. And we are going to calculate one interval at 95%. Okay, so here's what we get. All right. So we calculated one interval. Our sample mean was 17.299. Here was our sample of 100. So this is our sample data, and this is the mean of those 100 right there. Okay. All right. So from our sample of 100, we had a mean of 17.299. And then we look over here where our interval, it gets graphed out. Okay, that little black dot there represents 17.299. And then the green, we added a green to the right of our sample mean and to the left of our sample mean. That range represents our confidence interval. Okay. But I'm teaching right now. You need to go. Go talk to mommy. Go. Go watch TV. Bud.
There's a wasp in our playhouse.
Well, go.
It was about to come get me.
Go in the living room. I can't help you right now. Go in the living room. I'll come out in a minute. Sorry about that. You know, kids. That's 2020 for you, right? Yeah, my son peeked in and was scared about a wasp, so I do apologize for that. So this little green line represents our confidence interval. We have our sample mean, we added some for our margin of error, we subtracted some for our margin of error, okay? And then that black line is our population mean of 18, okay? So our interval, it does cross 18. So we took our sample of 100, one of them, one sample of 100, and it contained our population mean. So it was a good confidence interval, okay? So let's say we do it again. Okay, so now we've done another one, and it also contained our population interval. This one, the sample mean was 17.228. When we add and subtract our mean, or add and subtract our margin of error, it contains 18. It crosses 18. Okay? Now, instead of just doing 1, let's do 100. All right? So we have done 100 intervals, and so we have 100 of these lines over here. All right, so we'll start at the top. The first interval we got does cross 18, so it does contain our population mean. The second one does as well, third one, fourth one. And look, our fifth one does not. So this applet turns red. Okay? And if we look at all 100 of them on the spectrum, we have 1, 2, 3, 4, 5 of them that are inaccurate. 5 of them do not contain that population mean of 18. Okay? 5 out of 100 is 5%. That means that 95% of them do contain the population mean. All right, what was our confidence level? 95%. The red lines represent a confidence interval that does not cross 18. So like this one right here, all right, that's not the right one, right here. Okay, you can see the numbers there. It goes from 18.075 to 20.292. That particular confidence interval does not contain 18. And 18 was our population mean. Okay, we want our confidence interval to contain 18. And if we do that process, draw a sample of 100, because that was our sample size. If I do that 100 times, so I draw 100 unique independent samples of size 100, 95 of those 100 will contain our true mean, okay, our population mean. That's where the 95% comes from. I wanted to illustrate that for everybody. Of course, I have my running total that has a little bit more because I did those first two just showing you the one at a time. So that's what the 95% means. So if you're asked to interpret a confidence level, you would say, if we were to repeat this process many, many times, which is what I've done here, 95% of the resulting confidence intervals would contain the true mean of 18 or whatever. Okay? That's where the 95% comes into play. All right, now if you were asked to interpret the confidence interval, that is what we talked about in the conclusion. We are 95% confident that the true blah, 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 etc. Okay? So that is where that comes into play. I think this applet is just beautiful in showing that because it'll automatically do it for you as many times as you want. Okay, I could do it 10,000 times. Okay, and look, right at 95% of all of these confidence intervals. I mean, I can't even barely zoom in because there's so many of them, are good. Okay, so if we increase our confidence level to 98, all right, it changes to now 98% of them include our confidence interval because we're increasing that margin of error. When you increase your confidence level, that increases your margin of error. Okay? That's one of those connections. Those have a normal correlation with each other. So yeah, that is how. That is what that confidence level itself represents. Okay. Oh, I refreshed there. So means, normal, t, 18. What did I say? Like 5 sample. Okay. So yeah, I get my 1 sample. All right, that one was right on the money. Okay. My sample mean was 17.921. I add my margin of error, I get 18.9. I subtract my margin of error, I get 16.938. That one does contain my 18. All right, and then if I do it 100 more times, okay. Oh, look at there. That one we only had 1. So actually, it was worked 99% of the time. But then as I keep sampling more and more, notice that my total gets pretty much hones in right on 95. Okay, you end up with 5% of our intervals don't contain the right amount of data. So that is what the 95% means. If I were to repeat that process over and over and over again, we would end up with 95% of the resulting intervals would contain the true mean. Okay, so that is where we are on that. Okay. Cool. Let's go back to the slides real quick. I think we have our activity coming up next. Yes. So our example. All right. So we're going to collect some data here. We got a handful of us here. We can do this. So use the QR code. I'm going to put the link in the chat as well, and then use the class code that is on the slides. All right, and I would like for you to enter the number of letters in your first name. That is the data that we are looking at collecting. The number of letters in your first name. And I'll give everybody a second to do that. I have to allow you to. All right. Should be good. Data collection is enabled now, so you should be good to enter in that data. Okay, cool. All right. Hopefully you're seeing the dot plot populating on your screen. Is anybody having issues? It takes a few seconds for your data to go in. So let's see where we are. All right, I think we are probably pretty good here. All right, so now what we are going to do. We are going to create and interpret a 95% confidence interval for the true mean number of letters in first names in the U.S. Okay? So that is what we're going to do. And I'm going to show you kind of the best way to do this on your paper. I am making note of this, and we will move on in just a second. Should have had that rewritten. Okay, so here is what we're going to do. I'm going to show you the data. All right, so let's see. And I'm going to show you what my paper looks like. Okay? All right. So we have our data pulled in. Okay. And we have our problem. Okay? So what we're going to do, so here is our prompt. Create and interpret a 95% confidence interval for the true mean number of letters in someone's in first names. Okay? So whenever you see that phrase, create and interpret, here's the best way to do this. And I kind of picked this up from Sandra a few weeks ago. Take your paper, the space you have to work out that problem, and do 4 quadrants. Okay? And this is where that 4-part thing is going to come into play. You want to state, plan, do, and conclude. Okay? So the first thing we want to do is we want to state, what are we trying to estimate? We're doing a mean, all right, which is important. So I'm going to use mu as my parameter. And I'm estimating the true mean number of letters in our first name. All right. So for confidence intervals, that's the only thing you want to do in that state quadrant. Just let the reader know what is it you're trying to estimate. All right. You want to make reference to the population by saying true mean, etc. However you want to do that. So the next thing you want to do is plan. Okay. That is where your 3 conditions come into play. All right. Random. We're going to assume students are selected randomly. Now, in our instance here, they're not. Okay, we are all involved in AP Stats. However, is being an AP Stats going to make you more likely to have a longer or shorter first name? No. So that random condition is met. Independent. All right. It is definitely, I'm not even going to say reasonable to believe, there is at least our sample size, you can see over here from our data, is 8. Down on the bottom, down the bottom right, you can see the sample size is 8. So it's reasonable to believe there's at least 80 people. Okay, that is very clearly true. And then normal. All right, now this is one of those special cases. Our population is not normal. That was never given, okay? Our sample size is not large enough for the central limit theorem. So what I'm going to do, I could enter my data into my calculator and draw a box plot, 4, 4, 5, 6, 6, 6, 6, and 7, and sketch a box plot and draw that. I'm going to draw it right here, okay? So we got all right. Now I know my Q2 and Q3 are the same. They're one and the same because our data is so small, but there are no outliers and there's no strong skew. Okay. So that's what you would want to do there. You would want to enter it in your calculator and sketch out the box plot, show what it looks like, make note that there is no outliers and there's no strong skew. So that's my plan quadrant, okay? State, let the reader know what it is you're trying to estimate. Plan, do your 3 conditions, your 3 assumptions. Some teachers use that verbiage. And normally random is given the problem. We're collecting data live here, so it's a little bit different. But you know, we're just assuming they're randomly here. Normally you have a, quote, random sample of 65 students or whatever. Or sample size times 10 for your population. Make sure that's reasonable to believe, which it clearly is. And then your normal central limit theorem didn't apply. Nothing in the population says normal in the problem. So we had to draw our box plot, which the app we're using here does that for us. So then the next thing is to do our test. Okay. In this case, we are going to do a t-test. Okay, that is what we are going to do. Your formula, all right, if you were to do your formula, I'm not saying you have to do this because I'm going to show you how to do it in the calculator in just a second. T star standard deviation over the square root of n. Our x bar is 5.5 based off of our summary statistics. Our t star is going to be based off of the 95% and our sample size being 8, which I'll show you how to do that in the calculator in just a second when I swap over. And then my standard deviation was 1.069 divided by the square root of 8. All right, so to get the t star in our calculator, okay, we are going to go second distribution. We've used that normal CDF a lot. We are going to use normal CDF and inverse normal. We use for proportion, since we're using a Z curve, we did inverse normal. We are going to use inverse T since we are doing a T interval. For 95%, the area to the left is going to be half of 5%. And then my degrees of freedom, which I do need to make note of, is n minus 1, which is 7. Okay. And paste. And I get 2.365. All right, so that is what my formula is going to look like for my test. You do not have to do the formula on the AP exam. Okay, I'm showing you that in case your teacher wants you to show the work. I personally don't think that that's necessary. What I would do is I would go to Stat, go over to Tests, and option 2 is a one sample. Oh, no, that's a test. We don't want to do tests. Whoops. I'm sure somebody corrected me there. This is going to be a T interval. We're not doing tests yet. I was working on the slides late last night, so I'm still in test mode. Okay, so it should be a T interval. Yes, you could use 0.975 for the inverse T. That would work as well. That would give you a positive 2.365, but the positive negative doesn't matter because you're adding and subtracting anyways. Okay, that is a good point. Okay, so we are going to go not to t-test, and I fixed that on my notes as well that I'll pull back up. We are going to go to t-interval, which is down at option 8. Okay, I could input my data in L1. Okay, since we see that the 4, 4, 5, 6, 6, 6, 6, and 7. But since I do have the summary statistics, I'm going to enter those in. My sample mean was 5.5. My standard deviation was 1.069. My sample size was 8. My confidence level is 95%. Okay, and then calculate, and I get my answer. 4.6063, 6.3937. Okay. So this is what your do section should look like. Now, okay, again, I want to stress this because if you end up doing something incorrectly on the formula part of things, if you end up doing something incorrectly on the formula part of things, that can count off. So like if you wrote the wrong t-score, it could count off. So really, this is not necessary. I'm just showing you that. That's where it comes from. That is maybe your teacher requests it or requires it. But for the AP exam, you can write t-interval, degrees of freedom 7, and then your answer. And the degrees of freedom is sometimes necessary, sometimes not. It's one of those things they kind of go back and forth on, but that's easy to write, okay? And then our last thing is our conclusion. We are 95% confident that the true mean number of letters in first names is between 4.6063 and 6.3937 letters. Okay, so that is everything. All right, that is the whole kit and caboodle there. You got you referred 95% confidence because that's what the problem required. Okay, which I can pull that back up a little bit there. And we made reference to the true mean. And we had our answer in context. Okay, so we had number of letters in your first name. Okay, so that is everything you need in order to get full credit if that would have been a question. Typically on free response questions on the AP exam, there's a part B that has you do something extra that may or may not really be a stats concept. It's just more of a logic thing, like the Coke question we looked at 2 weeks ago. Okay, very similar to that. So yeah, that is it. That is how you would go through a full setup. I like that 4-quadrant method that Sandra represented. It keeps you on track. It gives you a plan when you do encounter the create and interpret a confidence interval, or like we'll look at next week, do the data, give convincing evidence, etc. Okay. All right. Cool. Let's wrap things up here. So I have it in the slides, so if you go back and look at that, you can see it, but I wanted to show you on paper what it should look like. So our do, our t-interval on the calculator, we went through that. Our conclude, I left the answers blank because I didn't know what our data would look like. All right, so your non-negotiables for this unit. Be able to prove normality for means, and again, there's those 3 ways. Central limit theorem is the easiest. Population normal, second easiest, and then what we had to do on our problem, sketch out a box plot to show it somewhat symmetric. I can My camera keeps freezing. That's very annoying because I have strained looks on my face. So yeah. Be able to calculate a t-interval for means. We did that. Also, if it's 2 means, you would do a 2-sample t-interval. But it's a very similar process like we did with last week on the 2 proportion. Be able to identify them for means on multiple choice without being worked out. That's sort of what we did with the formula. We were able to pick out the t-score, pick out the standard deviation, the sample size, all that stuff. Understand what the confidence level means. That's what we looked at with the applet. If we were to repeat something several times, 95% of them would contain the true mean. And the difference, that's how you interpret the confidence level. If you're asked to interpret the confidence interval, that's what we just did with we are 95% confident, ... Also be able to pick out the degrees of freedom for a t-interval n-1. Okay, right now degrees of freedom is n-1. It's a little bit different with chi-squared, but more than likely t-intervals are more common than chi-squared. So, yep, so n-1. All right, awesome. Hop on over to Discord for the after party as we break things down. Also, if you ever have any questions there, we can answer those. Sandra does a fantastic job of keeping up with all of that. And we will catch you all next week, next Saturday at 2.